So let's get started. Last time, on Friday, we proved Lagrange's theorem, which stated that if G is a finite group, then and H a subgroup of G, then the number of elements of H divides the number of elements in G. Now there is one small mistake in the notes that I've written. There is one place where I say let x1 up to x1 equal E, x2 up to xk be the representative of the equivalence classes. Could you please look at this? In the proof I said let x1 equal E, x2, x3, xk be the representatives. Do you see it? Okay, please remove the the. The is not correct. Okay, let x1 up to xk be representatives. Okay, they are not the representative, they are representatives of the distinct equivalence classes. Okay, great.
Let x1 equal to E, x2.
Yeah, be the representative, you just remove the.
Okay, so it's like the part just before we explained that kh is equal to G, right?
Yeah, exactly, yes. Okay, great. Let's get back. So if G is a group, if G is a finite group, and H a subgroup of G, I've used this notation, a subgroup of G, then the number of elements of H divides the number of elements of G. Now corollary, if G is a finite group, and G is in G, then the order of G divides the number of elements of G. In particular, I'll add this one. G, the number of elements of G is equal to EG. Now, last time we proved we saw that G has finite order if G is finite. Now we'll have to prove that the order of G divides the number of elements of big G. Okay? The number of elements of a group, we usually call it the order of a group. Okay, when I say the order of a group means the number of elements of a group. Okay, great. Okay, last time you remember this, we saw this. Now I'll just prove that the order of G divides the cardinality of G. Great. So consider the set G to the n is in Z, and n is strictly between okay? So what I'm really doing here, I'm taking all the powers of G, so G to the 0, G to the 1, G2, up to G or G minus 1. And G to the 0, of course, is the identity. What can I say about these elements? this, they're all distinct, right? Do you see that? Do we see that they're all distinct? Yes? Because the elements in the set S are all distinct. I think last time I used the S, let me call it something else. I don't know, set T, let's say, are all distinct. Should I leave this as an exercise, or do you see why they're distinct? You see why they're distinct, right? Because the order, if you have two of them that are equal, then the order must divide the difference. And that can't happen. Yeah? You see that? Let me prove it. I mean, you know, let's if xy are in 0, 1, up to 4g minus 1. And g to the x is equal to g to the y. Then g to the x minus y is equal to the identity. So far so good. Yeah? Then the order of g will divide x minus y. Yeah? This is the property we saw about the order. If you have a g to the something equal to the identity, then the order of g divides x minus y. Now what can I say about x minus y? xy is in 0, 1, strictly less than order of g. So 0, x, strictly less than order of g. And y, 0, strictly less than order of g. So x minus y is less than the order of g, strictly less, and strictly bigger than minus the order of g. And if x minus y divides, if order of g divides x minus y, then what's the only number that is divisible by order of g that is strictly between minus order of g and order of g? 0, right? So the order of g, so x minus y is equal to 0. So x is equal to y. Okay? So if you have that gx is equal to gy, then it must be the case that x is equal to y. Hence all of these elements are distinct. Great. Now I claim these form a subgroup. Yes, sir?
So just to clarify, on the gx equals gy part, we left multiplied by g to the
Minus 1.
y.
G to the, what am I, yeah, g to the y minus 1. Exactly.
Okay, and that was equivalent to g to the y inverse. G to the y inverse.
Exactly. G to the minus y, or g to the y to the minus 1.
And that's all.
Yeah. So g to the y minus 1. Okay? Yeah, sir. Are we good? Okay. Okay. Now I claim that these form a subgroup. Do you see this? Do you see that these form a subgroup or not? This is a subgroup. The set T is a subgroup. Do you guys see this or not? Take any two. Take any two of these. Multiply, okay. So clearly EG is in T. EG is in T. Suppose that G of S, well, we know G of S times g of t. What is that equal to? Well, let s and t be 0, 1, up to order of g minus 1. gs gt, what is that equal to? This is gs plus g, right? Yeah? You see that? Now, reduce s plus t modulo the order. So, let R be such that 0 R order of g and s plus t is equal to q times order of g plus R. Write down the Euclidean division of s plus t and R. Basically, we're reducing s plus t modulo R, and you get that this is g to the R. Are we good here? Do you guys see this or not? Is it a bit quick or? Okay, so what is g to the s plus t? G to the s plus t is just g to the q order of g plus r, which is just g to the order of g to the q times g to the r.
So, since s plus t are both like in that interval of, well, in the set like 0, 1, order
Yeah.
of g minus 1, isn't q gonna be 1 anyways?
S plus t.
Yeah, but s plus t is smaller than 2 times the order, so if you remove, if you
So
just
s
subtract-
plus t. So for example, take s, so g4.
Yeah,
So let's say g5 is 1. Okay? Say the order is 1. g4 times g4, this is g8. Okay? It's a bit bigger than 5.
yeah, but it's like you don't have to do the module if you just subtract the order 1.
Yeah, exactly. Yes, but I'm doing it more general. You mean like, do it here.
Yeah, I mean,
Yeah, exactly.
q is gonna be 1.
I understand. Yes. But this works as well. I see what you mean. Like you say that the remainder of this q here is 1. Sure. Yeah. We can do that if you want. But I mean, this is still correct. Very good. Yeah. And then what do you get? You get g to the r. Okay, so this is a group. Now to check the inverse. The inverse of g to the s, g to the s inverse, what is that? This is g to the minus s, which is just g to the order of g minus s. Okay? And order of g minus s will be inside this interval. Okay? Are we good? Yeah, is it clear? So this set is a group, and T is a group of order k, and T is a group with k elements, with or g elements. By Lagrange's theorem, what can I say? The number of elements of T divides G, hence the order of G divides the number of elements of H. Okay? Oops. Great. Awesome. Hence, hence what? Hence G. Okay, yeah. So if the order of G divides big G, and it's also the case, is EG to the K, which is G. Okay. Are we good here? Where? since G, the order of G divides the number. So this is because the order of G divides the number of elements of big G, so you can write this. Okay, great. This is the proof of Lagrange's theorem. Is it clear? So can a group of order 7 have an element of order 5? Can a group with 7 elements have an element of order 5? Yes or no? No. Suppose I have a group of order 11. What are the possible order of elements? 1 and 11. Very good. If I have a group of order 6, what are the of a group with 6 elements? What are the possible order? 1, 2, 3, and 6. Very good. Now a question is that a good question to ask. What about the converse? Is the converse true? If I have a group of order 12, do I have an element of order 6? Or do I have a subgroup of orders with 6 elements? Or all the questions like that are kind of, the reciprocal of these statements. And we will answer these questions. We will see maybe on Monday or tomorrow that in some groups you can find an element of some order. Okay? Well, that doesn't help, but you can. So for example, let's say if you have a group with a number of elements divisible by a prime p, then there is a theorem that tells you that you have an element of order p, if p is prime. We'll see that. Okay, great. Any question on this or not? Any questions on this? I mean, it's a proof. You should know the proof. And that's it. Okay? Please know the proof. The proof is important. From the beginning until the end. Yes? Yeah, exactly. Exactly, yeah. All the proofs are this proof is very important. Okay, great. Now we introduced left cosets. We will introduce now right cosets. We saw that the left coset. Homework 4 is posted, right? Did I post it? Or okay, yeah. For homework 4, I think none of them is one. I think I put 5 problems, but 1, 2, 3, and 5 are not due, right?
Yeah.
If I'm not mistaken. And 4, I tell you 2 questions that are due, and the remaining 2 I'll pick. Okay, so it's really a lighter workload if you wish to, take a small break. But please, number 4, please do take it seriously. Okay, try to spend time on it. It's gonna follow us a lot. Okay, it looks difficult, but it is not. Okay, it looks long, but it's not really long. It's 2-3 lines each answer, 2-3 lines each answer, 2-3 lines each answer, and then that's it. Okay? Great. So we saw that a left coset is a subset of G of the form x and h for some x in G. Okay? A right coset is a subset of G of the form h times x. So you take all of the elements of h and you multiply them by x on the right as h. Now we will kind of do the same thing for right and left cosets. And I will not prove everything, of course, because the proofs are similar. So consider the following relation on G. I'll call it R here, you know, right, basically for right. Say that X is related to Y if XY inverse belongs to H. Of course here H is a subgroup of G. H is a subgroup of G. Okay, so for the left coset, what did we have? We had X inverse Y belongs to H, right? You remember this? For the left coset, the equivalence relation was X is related to Y if and only if X inverse Y belongs to H. This relation is an equivalence relation. On G. By the way, there's something. Tutorials, I've heard that they're getting a bit less full, a bit emptier, I guess. Please, it's important that you attend, okay? Who attends the tutorial? Just if you could raise your hands.
But I know there was tutorials.
Oh, there are tutorials, okay. So please do attend them, okay? They're important. At least attend one. I mean, you know, you're supposed to attend one. Try to do your best to attend one. And I think,
why should we attend one?
I mean, you know, it's and I think a lot of the questions from the homework are actually in tutorials.
No, it's not.
So like, really?
No, it's not. I did that. I go to the ultra on Monday. Nah, that's not true.
Pardon me?
It wasn't tutorials, they're like from the textbook itself in this part.
Yeah, but I'm pretty sure I've seen some of them. Some of them in the homework are in the tutorials. No? Show that x squared is equal to the identity. If x squared is equal to the identity for all x, then G is a billion. That you have seen in tutorials, no?
But it's not all the same tutorials.
Yeah, but I think 2 of the 3 tutorials did it, no?
No, currently not.
I'm okay. Anyways, but do attend, okay? Please do attend the tutorials. I mean, Jillian, William, and Antoine are being nice and posting very nice notes, but that doesn't mean I think they're doing a better job than posting their notes. But again, that doesn't mean you should not attend. Okay? Yeah. So please attend. I mean, you know. We'll see if I take a question from the tutorial of the midterm and I take it from tutorials. We'll see that. Okay, maybe I take a question done in tutorials and put it on the midterm. That way it's, I make it interesting. Okay, great. Awesome. Okay, so this is an equivalence relation on G. I'll let you show it. Now what's the equivalence class of X? It's the set Y in G such that, just let me do it so like that. You know, it doesn't really matter. Such that Y is inverted in H. So it's the set Y in G such that Y is equal to X inverse, Y X inverse is equal to H prime for some H prime in H. So what is this set? This is the set. So this means that Y, all the Y's that can be written in the form H times X. So this is just the set H times X, as H is in H, G is just H times X. Okay? The same proof. Awesome. Am I going fast or it's
No, it's
yeah,
really
it's good,
similar.
right? I feel it's okay, right? But okay, so what can I say about any 2 right cosets? Are they any 2 right cosets are if these are the equivalence class of an equivalence relation, what does it mean? It means that any two right coset are either disjoint or equal, right? Very good. And what can I say about G? It can be partitioned into right cosets, right? Because these are the equivalence classes of the equivalence relation. Of course, I'll let you show that. It's the same thing we did like last time. This is an equivalence relation. I'll let you show this. I'll leave it to you as an exercise. The equivalence classes are the right cosets. And then G can be partitioned into disjoint, of course, right cosets. Now, in general, it is not true it is not necessarily true that XH is equal to. Okay? Great. So, I can partition G into disjoint right cosets. Great. Now, how many, well, first, is it clear? Is this clear? Is the same or yes, sir?
Yeah, this is the statement is true only for a billion groups? Or?
So if G is a billion, then this statement is true, right? That's a good point. If G is a billion, then XH is equal to HX for all X in G. Okay? Now, you give a very good idea. I'll leave it to you as an exercise. I mean, this is a very good point. So if G is a billion, then this is obviously true. If you multiply all the elements of H by X on the left, it's the same thing as multiplying all the elements of H by X on the right, because HX is equal to XH for any little H in H. Now, this is imposing a big condition on G. Now, there are conditions that we impose on H. And these conditions on H will call H a normal subgroup if this holds. But that will come later. Now, there is just small exercise. Consider the set NH. It's the set of X and G such that XH is equal to HX. So usually we call it NGH. Show that NGH is a subgroup of G. Okay? It's an exercise. Okay, now I'll write down some comments, some relations between right and left cosets. Proposition. Let G be a group. And H a subgroup of G. Okay, define the following two relations. Denote by, I'll just call this one left. X left y, if and only if y inverse x belongs to H. This is the equivalence relation we saw on Friday, right? I'll just call it left here because the equivalence classes are the left coset. And the right coset equivalence that G1 is related to G2. Well, I don't want to use G1. let's use S and T. You know, I could use X and Y, but that's okay. Just change the letter. S and T, if and only if S T inverse belongs to H. This is the equivalence relation or equivalence relation whose equivalence classes are the right coset. And the first relation is an equivalence relation whose equivalence classes are the left cosets. Great. Then, the following are equivalent. The following are equivalent. One, well, let H be a subgroup of G, and G1, G2 being G, the following are equivalent. G1H is equal to G2H. 2, G2 inverse G1 belongs to H. And 3, H G1 inverse is equal to H G2 inverse. Okay, so let's prove this. The proof should not be these proofs should be very quick proofs. Okay? Let's have a look. So I will do just 1 is equivalent to 2 and 2 is equivalent to 3. Okay, I'll just do this. How is this done? So I'll just do 1 is equivalent to 2 here. So G1H is equal to G2H. What does it mean? What is the left coset that we get by multiplying everything on the left by G1? This is just the equivalence class of G1 under the left equivalence relation, right? And this is just the same as G2. Now if I tell you that yeah, are we good here? Yeah, are we good? Yeah? Great. Now if the equivalence class of G1 is equal to the equivalence class of G2, this happens if and only if G1 is related to G2 on your left. Right? If the equivalence class of G1 is equal to the equivalence class of G2, this is equivalent to saying that G1 is related to G2. Yes, sir? Left coset, you just multiply everything of H on the left. On the right, just multiply everything on the right. Okay? You multiply all the elements of H by X on the right. Yes, sir?
How can you go from an equivalence relation to like a coset?
Well, the coset is an equivalence.
Oh, fair.
Yeah, right? The coset is an equivalence class. So G1 is the G1H is the equivalence class of G1. G2H is the equivalence class of G2. So saying that the equivalence class of G1 is equal to the equivalence class of G2 is equivalent to say that G1 is related to G2. Now what is it? It's equivalent to say that G2 inverse G1 belongs to H. Great. Let's do the same thing here. Let's show that 3 is equivalent to 2. So if I have H G1 inverse is equal to H G2 inverse, this means that the equivalence class of G1 inverse under the right, under the second one, this one, is equal to the equivalence class of G2 inverse under this one. This means that G1 inverse is equivalent to say that G1 inverse G2 inverse. Now what does this mean? This means that G2 inverse, G1 inverse, right? ST inverse, right? ST T inverse. So you take the inverse of the second one and you keep the first one fixed. Okay, so this is equivalent to T2 inverse G1. It's a bit fast and it's a bit short, but it's a nice way to see this, to work with cosets as equivalence relations, as equivalence classes. So, okay. So here we're using the fact that if two equivalence classes are equal, then the elements, then the representative must be related, right? These are stuff that you have seen before. We remember this or not? Yeah? Okay. Great. Now, why am I doing this? Well, the question is that how many left cosets do we have? How many? So, how many left and right cosets do we have? You know, if G is finite, for example, then there are the number of elements of G divided by the number of elements of H left cosets of H, right? Now the theorem here will say that the number of right cosets is equal to the number of left cosets. Or in other words, to prove it more generally, there's a bijection between the left cosets and the right cosets. And the bijection is given here. You can see it immediately. I'll erase this one here. Okay. So we use a small notation now. So we denote by G modulo H the set of left cosets, and we denote by also its, well, or not to pronounce it, the set of right cosets. Okay. Proposition. There is a bijection between G mod H and G mod H on the right. Okay, G mod H, this one is just the set of left cosets, and H and G mod H on the right. So this one is the right cosets, this one is the left cosets. And there is a bijection between these two. I'll call it phi. That sends a coset GH to H G inverse. Now one might be tempted to send it to HG, right? Send GH to HG, but that might not be a well-defined map. GH might not be as H. Might not be well defined if you send it to HG. If you send it to HG. Well, however, if you send GH to HG inverse, this map turns out to be a well-defined map. Okay, should I prove it or leave it as an exercise? Should I prove it? Yeah. Proof. Phi is well-defined. Suppose. So what does well-defined mean? Suppose that G1H is equal to G2H. You need to show right? So that, right, this is what well-defines mean on equivalence classes. That it does not depend on the representative you choose. Right? Yes? H is a subgroup of G, yeah. Okay? Is the concept of well-defined clear? It's not an easy concept, but you should get used to it as well, okay? I mean, when I took my first algebra course, I didn't know what it is. So I just, yeah, okay. You just construct functions and then you say, yeah, this is a bijection. I think I wrote that at some point and it just gave me a 0. Like a, the grader I think didn't read, you know. I did something like that, GH to HG, and then the grader just didn't read. 0, okay? So it's totally natural not to understand it. But again, you should practice it, okay? So, why is this true? So, we proved this before. So if G1H is equal to G2H, this is equivalent to saying that G2 inverse G1 belongs to H. Technically what you can do, just say G2 inverse G1 belongs to H, and this is equivalent to say that H G1 inverse is equal to H G2 inverse. This is by the previous part. Okay? If G1 is, so phi is well defined. Now, could you write down an inverse for phi to show that phi is bijective? Could you write down an inverse for phi to show let tau from H that sends a coset, a right coset hx to x inverse h. Also, tau will be well defined by the same argument, and just look at phi of tau. Okay, phi composed with tau, and tau composed with phi. Okay, continue the proof. Okay, we should be easy, right? Tau composed with phi, you get back to. So take tau of. So take phi of. Let this just be. No, I mean, try to do it, okay? Try to do it. Try to do it. It's a good exercise. So this is one way to prove it's bijective. You find an inverse for it. I found an inverse, and then show that phi composed with tau is the identity on this one, and tau composed with phi is the identity on this one. Okay? It's not bad, right? You're just using that the inverse of x, that x inverse is equal to x. That's what you will be using. Okay? Is it clear, or should I do it? Should I do it? Should I just do it? Phi tau of xh, what is that? Phi tau of hx is equal to phi. What is tau of hx? This is phi of tau hx. Tau of hx is x inverse h, so this is phi of x inverse h. Now you send gh to hx, right? Phi sends gh to hg inverse, so it sends x inverse h to hx. And then tau. So phi composed with tau is equal to the identity on g naught h, and tau of phi, tau composed with phi of xh is equal to tau of what what's phi of xh? It is hx inverse. Hx inverse is that x h and tau composed of phi is the identity on G mod H. So tau is invertible. So phi is invertible. Phi and tau are invertible. And are bijections. Okay, so the number of right cosets is equal to the number of left cosets. It's a bit quick, but yeah. Yes?
That would be opposite that phi dot tau is the identity of G. So that's what I like.
Okay, how did it find phi? Tau. Go. Yes, okay. Great. Hence, there's a bijection between G mod H on the left and G mod H on the right. Okay, great. It's a bit well, it's not the easiest, but anyways. Okay, well, we have 2 minutes left. Yeah, I mean, I don't want to, well, let's see if I can start. Yeah, no, it's a bit difficult. Okay, so I'll see you on tomorrow, 12:05. There is from 6:30 to 7:30, there's a small exercise session, okay? I help you with proofs and things like that. And if you have questions, you can ask me.
6:30 to 7:30?
Yeah, I'll record it, yeah.
Where is it?